Hey folks, Todd Coburn with your Aerospace Structure series. This little video will solve for the slope and moment of a beam using singularity functions. Enjoy. Here's another example. Given this beam here, once again we look at this thing and we say, oops, we're going to have to characterize this loading because it doesn't go, this distributed load doesn't go to the end of the beam. Looks like a simple characterization. So we start off by taking that 8 kilonewtons per meter and driving it all the way to the end, because once you turn those puppies on, you can't turn them off without giving it a cold shower, as you see down here, the minus 8 kilonewton per meter. We also don't forget you need those reactions. That wall at the left end imposes a constraint on both the vertical deflection and the moment, so both of those are going to be needed. You're going to need to calculate those values. To solve this, then you can, once you have a free body diagram showing everything, you can move from left to right and write the singularity function for each and every thing you find. Starting with the shear force, that's our first term. The moment, that's our second term. The distributed load that goes to the end, that's our third term. The moment at B, that's our fourth term. And then the cold shower distributed load, which starts at point B, that's our last term. We then can integrate that puppy and note that any constant of integration will be 0. Notice that we didn't write a function term for that 12 kilonewtons since it's the right end. We integrated that puppy and ignored the constant of integration since it's going to be 0. Integrate that puppy again and ignore the constant of integration since it's going to be 0. That gives us the moment. Now to calculate the slope, we're going to divide that moment by EI as we integrate. First, we're going to simplify like this. Okay, now we integrate again. That gives us the slope, and integrate again. That's going to give us the deflection. We've got two undetermined constants of integration. Now, we could have made this a little easier. After getting the equation for the slope, we could have plugged in that the slope at 0 is 0 and immediately gotten what C1 is. Or we can do it later, noting that the slope is 0 at x equals 0. That gives us that first one, and the deflection at 0 is equal to 0. That gives us the second one. Rewrite and simplify. That gives us the equation for the deflection. Got it? Now, wasn't that amazing? Enjoy.